Well, you might be getting tired of titrations. So, if so, no problem. This is our last one, at least in this chapter. And what we're going to do is have you do the titration this time, since we've learned how to do it already. We're going to do the titration of carbonic acid. And the previous chart that we looked at said that carbonic acid has a pKa of about 6.3. Now, it turns out carbonic acid is a diprotic acid. That means once you've taken one proton on, there's still another one to take off. And I'm going to give you a little hint. You could look it up yourself, but the next proton is going to come off at 10.6. And so you can go ahead and fill in everything on this page now. I want you to draw the appropriate structures after we remove one and then two protons. I want you to label those with letters. I want you to divvy up our titration curve down here in the appropriate manner. Label the x-axis and the y-axis. Fill in your curve. Do everything we did before, including where are the buffering ranges? Label them. Where is blood? pH 7.4. Does it sit in a buffering range? What two species of the ones you drew at the top of the page are in blood? Which one of them is there more of? These are the questions I want you to answer. Let's see how you do. Pause it, take 5 or 10 minutes to do this, then turn it back on again, and let's see how it looks. Okay, let's get back up to the top of the page and see what we have. First of all, if we take a single proton off by challenging it with sodium hydroxide, we have one left and one is going to be a sodium salt. Now, you might be tempted to call this monobasic carbonate. Not a bad name, but we don't call it that. We actually call it carbonate. In fact, we call it sodium bicarbonate in this case, and that is baking soda. It's the same stuff like Arm & Hammer baking soda that you maybe have in your house for baking needs. It's in our body, and it's also a pharmaceutical agent. It can be given to people in the emergency room. So that gets us A, B, and then there's one more, C, and that's going to be the one where we've taken both protons off, and that would have 2 sodium. We'll go ahead and put those on there this time. Na2HCO3, and this is called carbonate. So those are our 3 species, A, B, and C. And let's go ahead and sort out how we do the titration. First of all, we're going to be measuring the pH, and we're going to do so as a function like we did before of sodium hydroxide equivalents. How many equivalents do you need to divide your graph into? 2 protons, 2 equivalents. Let's go ahead and go right across like that, 0, 1, and 2. Now, remember how we started these? You don't start all the way on the left. You start at the first midpoint of the first equivalent. And we're going to go up to 6.3, right at that equivalence, or midpoint equivalence. And we're going to have a nice gentle slope going up like that. We're going to do the same for 10.6 at the midpoint of the second one. Going to have a nice gentle slope going up like that. We're going to go concave down on the left sides and concave up on the right sides like that. And that is our titration curve. We can go ahead and say carbonic acid is going to dominate way down there. Bicarb is going to dominate right here in the first equivalent, and carbonate, the doubly deprotonated carbonate, is going to be way out there at the end. Okay, that's our titration curve. Let's go ahead and load in our buffering ranges. It's going to be 5.3 to 7.3. We'll draw those as carefully as we can. And it's going to be about 9.6 to 11.6. So where is blood? Blood is at 7.4. Let's do it with green again so we can see. It's going to be right there. Well, that doesn't seem like it's formally within the buffering range. That's absolutely true. It's not quite within the buffering range, but we'll come back to that in a little bit. Let me ask you, what two species are in blood and which is there more of? The answer is A and B. Look where we are. We're in the process of titrating from 100% A to 100% B, and we're closer to B. What that means is we have more of B. How much more? Well, that's coming a little later, but for now, let's just leave it at that. There's a lot more B because we're closer to 100% B than we are to 100% A. Here's an interesting question. Would this be a better buffer for acids or bases? Well, let's consider that a little bit. If I was sitting at blood and I added acid, the pH would be flatter for longer than if I added base. That's interesting. This is not an ideal buffer. The blood pH is not right in the middle. So this actually has better buffering capacity for protons, acids. And actually that's one of the reasons why this is so good, even though it's right up there, just almost outside the range of the buffering range. We have a bigger problem in our body with too many protons. And this is really good at buffering protons because there's a lot of flat area out there. However, we don't want the pH to change at all, and it looks like it's going to change whether we add protons or base. So, why is this such a good buffer for blood when it's not even quite in the range? Well, one of the reasons is the concentration. The amount of bicarb we have in our blood is 25 millimolar. It's about 50 times higher than phosphate. So let's just make a note of that. Good capacity. You got a lot of base in your blood, a lot of bicarb, and that means it's going to be able to soak up a lot of protons as a neutralizer. The other reason it's such a good buffer for blood is a complex, strange phenomenon about the structure and reactions of carbonic acid. And I'm going to pick that up on the next page and show you something extraordinary about blood pH, and of all things, about your breathing.